Hey everybody, so we're going to start this new unit. Hope you're staying warm this weekend. And if you are checking this out with me, this looks very familiar, so no curse words, please. We already know that moles live here in the middle, and you should know that there's always one mole when we are dealing with one of these cute little things that I like to call the molar roadmap. And if you'll remember, we had our little balloon up here, and our balloon held 22.4 liters of gas. And then down here, we had our scale where we said that 1 mole was equal to the number of G units in that chemical, which depended on the periodic table. And then down here, got a little confusing in the last chapter, but we basically said that 1 mole has 6.02 times 10 to the 23rd representative particles, molecules, atoms, ions, whatever we were talking about. Okay, so we're going to keep it simple today. We're not going to get into nitpicky atoms, ions, and all of that. We're just going to go with standard form. So here's where I told you a big fat lie. This number right here. It's always a 1 if you stay inside this box. But here's the trick. Now we don't have just 1 box. Now we have 2. And so the difference in what we have done before and what we're going to do today is we're going to switch from chemical A over on the left side over here to chemical B. And when you switch from chemical A to B, you use this pathway here in the middle. This pathway here in the middle is called your mole-to-mole ratio. And we're going to use the coefficients from the balanced chemical equation to tell us what that ratio is. So we have a big fancy name for this mole-to-mole ratio business. It's called stoichiometry, which is quite weird, and kids usually say that it's icky. Get it? Look at your notes, and we look at the definition up at the top of stoichiometry. We find out that stoichiometry deals with the mass relationship among reactants and products in a chemical reaction. It lets us predict how much reactant we need to produce in as a product, or how much product we can expect to get out of a reaction based on how much reactant we use. So let me make this really simple. If we had reactant A plus reactant B to make reactant Q, it's basically a way of saying if I have 15 grams of A, how much Q can I make? Well, on the test that you took on Friday, for those of you who were lucky enough to get out of it, count your lucky stars, on the test you did Friday, I gave you the number for B. For example, if I had given you 5 grams, 15 plus 5 equals 20. But if I hadn't given you that number, if I hadn't given you that 5, then you wouldn't know that that was 20. So stoichiometry is kind of cool because when we don't know this number for B, we can automatically get the answer for Q by going from A directly to Q. And I'll show you how we're going to do that in just a minute. But that's what the definition means. It allows us to start anywhere in our equation and go anywhere else in the equation. So let me show you a different example. People always think that you always have to start on the left side of the equation and go to the right side, but that's not really the case. If I have A plus B making Q, the problem might say, hey, you produced 15 grams of Q. How much A did you start with? And so we can actually go backwards and jump anywhere around this equation that we want to go. So it is kind of neat. So check this out. This is the most important thing about this whole next week of your life. This mole ratio, it's a conversion factor. All that means is something like 12 inches is 1 foot. That's a conversion factor. Well, this is a new conversion factor that lets us go from the given amount to the desired amount. And mole ratios are derived from a balanced chemical equation. So that's what goes in this first set of blanks right here. Balanced chemical equation. And the ratio itself comes from the coefficient. That's the big part right there. So in this reaction, if we balance the equation, you're going to put a 2 in front of ammonia and a 3 in front of hydrogen. My fifth period's coughing and acting like turds on purpose. And this would be an imaginary 1. For the purposes of today, I'm going to stick that in there for you. So when I say mole ratio, what I'm saying here is that I have 1 mole of nitrogen for every 3 moles of hydrogen to create 2 moles of ammonia. So those coefficients represent a mole-to-mole ratio. So if we were comparing nitrogen to ammonia, the way we would set this up is either by saying there's 1 mole of nitrogen needed to create 2 moles of ammonia. Or you could flip it upside down and say to make 2 moles of ammonia, you need 1 mole of nitrogen. So these are our mole ratios. So back to our molar roadmap. So the good news is you already understand how to use the little Mercedes symbol of the roadmap. The only thing that is now new is now we've got to get from this chemical A over here to this chemical B by using that ratio that I just talked about in the coefficients. The other thing you're not going to be real happy with me about is I used to tell you whenever you were using mole, it always had to be 1 mole. Well, not anymore. If we go back to the previous equation where we had nitrogen plus 3 hydrogens making 2 ammonias, if we were actually going to be going from hydrogen to ammonia, you should notice using these coefficients, my ratio is 3 to 2. And so if we were going here, it would be 3 moles of hydrogen going to 2 moles of ammonia. You'll notice that neither one of those numbers is a 1. So only on this ratio step can your mole number be a number other than a 1. Now sometimes, like in the previous slide, it will be a 1 if we were using nitrogen and he's got a coefficient of 1. Well, of course, the word mole is going to have a 1. But just be aware that as we move forward with this, it's not always a 1. So let's go to example 1 in your notes. So down here, it says we are given some ammonium nitrate. There should be an arrow there. Not sure where that went. And it gives us some nitrogen, some water, and some oxygen. And it says how many moles of water are produced. So I always come over and I find the chemical that they mention. And they mentioned this water. And I put question mark moles, because that's what we want to know. How many moles of water are produced if 15 moles of oxygen, which is right next door, are also produced? And so I'm going to label that guy as well. So what freaks people out is that I'm on the same side of the equation. We don't always have to go from the left side to the right side. Sometimes we're trying to compare 2 of our products, like in this example right here. So we are literally going from our given, which is 15, to our water, which is here. So let me show you how we do this. We're going to follow the same steps we used to. We've got 15 moles of oxygen. Don't forget that 0.0 because that makes that 0 significant. Moles of oxygen. And we're going to train track it. Now at this point, we have to figure out What is it that we're trying to accomplish? Where are we going? What are we doing? So if you remember, going back to our molar roadmap, we are going from moles. Oops, sorry, I don't have a pen. I have an eraser there. We are going from moles to moles. So in this example, we're going straight to the mole ratio. If you take a look at our molar roadmap up here in the corner, we are starting here at moles of A, which was our oxygen. And we're going straight over here to moles of B, which is our moles of water. So for the first time ever, we're switching chemicals right in the middle of the equation. We've only ever had one chemical to deal with. But now that we've learned about reactants and products and balancing, now we can go anywhere in a whole chemical reaction. So same rules as all year long. So whatever's up here on the top left, moles of oxygen, needs to be down here on the bottom right, moles of oxygen. And then we're going to change that into moles of water, which is what we want. So if you remember, back behind my molar roadmap here, it told you, well, that's kind of interesting. It told you that the ratio comes from those coefficients right here. So when we were talking about that earlier in the video, we said that the ratio comes from the coefficients. So that's what we're going to do, is we are going to go grab our coefficients from the reaction. So when you look in the reaction, how many moles of oxygen do we have with that coefficient? Well, there's nothing there. So in this instance, it's indeed a 1. It's a coincidence. But when we go next door to compare it to the moles of water over here that we're trying to create, there's 4 moles of water because he has a coefficient of 4. So basically, when this reaction occurs, 4 moles of water get produced for every 1 mole of oxygen. So there's a 4-to-1 ratio. So our moles of oxygen in our train track cancel out, just the words, not the numbers. We're left with moles of water, which is what we want. You shouldn't even need a calculator for this, because you should know that 15 times 4 divided by 1 is indeed 60, but we need a 0.0 on that because of the 0.0 on the given. 60 moles of water. So that's the new step, everybody. We are allowed to switch chemicals, and we do it with that mole ratio. So let's try another one. Let's look at example 2. Oh, here's our equation that we've talked about already today. We've been given nitrogen plus hydrogen to yield ammonia. But look how example 2 is different than example 1. It says, what mass of nitrogen? So I'm going to come over here and put question mark grams. They want to know how many G units or grams of nitrogen was required to produce 35 moles of ammonia. So I come over here and I label 35 moles. Before I ever go down and start my train track, I try to figure it out using my molar roadmap. So whoever has the number is my given. So in this case, we're going backwards. We're given the ammonia, and we're trying to go back to the nitrogen. So if I were to label my molar roadmap up here, I'm starting here at moles of ammonia. That's chemical A, the first chemical we're starting with. They wanted grams of nitrogen, which is going to be down here because it's our second chemical, but they didn't ask for moles. So how do we get from moles of ammonia to grams of nitrogen? First step, we're going to jump. We're going to jump over here to moles. So this will be moles of nitrogen, which is chemical B. And then we'll go down and change it into grams. You already know how to do that step. That's not new. So look how many things I circled. 1, 2, 3. that tells me that I'm going to need 3 tracks. So if you can plot it on the map, you can automatically know how many steps you should have, follow the whole diagonal rule thing, and this shouldn't be that bad. So let's try it out. We've got our 35.0 moles of ammonia. We diagonal down and put moles of ammonia again. Now at this point, I would check my map and say, where am I going? I'm going from moles of ammonia, which is right here, and I'm going to jump over here to moles of nitrogen. And so I'm going to change colors to show you at this point we switched chemicals. Moles of nitrogen. And this is where we need our mole to mole ratio step. So anytime you have mole to mole stacked on top of each other, that's the step where we know that we might have things that are not a 1. So I find my moles of ammonia in my balanced equation, and it's 2. Find my moles of nitrogen in my equation. It's an imaginary 1. So I'm going to put my 2 on the bottom and my 1 on the top. There's my mole to mole ratio. Moles of ammonia cancels with moles of ammonia. Now we're in moles of nitrogen. So then I consult my molar roadmap again and say, okay, I'm here. Now I have to get down here. This was pretty easy. We know how to go from moles to grams. So same steps. I put moles of nitrogen on the bottom, and I put G units of nitrogen on top. This is the old rule. When you have moles and grams stacked on top of one another, this was the old step. What number always went with mole when we went from moles to grams? And the answer is a 1. This has nothing to do with the coefficient. It's just a coincidence that they're both a 1. Then how do we find our G units? Looking at the periodic table, nitrogen's a 14.007. We have to multiply it by 2 since it's a Hofbrinkel, and we end up with 28.014. So when you put all that into your calculator, you'll do 35 times 1 times 28.014, divide by 2, divide by imaginary 1, and the calculator says 490.254. I only need 3 sig figs, so we're going to cheat a little bit. 490. We're going to put a decimal at the end. That gets us our third one. Grams of nitrogen. Ta-da! You're done. Let's keep trucking. Flip it over on the back, Jack, and we've got 2 more examples, and you're done. So in example 3, a whole lot similar to example 2, just a little bit in a different direction, and the more of these you see, the better you'll feel. So check it out. It says, how many moles of hydrogen? So that's my question mark. So I go over here to hydrogen and I label it, how many moles are produced if 56.7 grams of sodium are added to water. So I label that with the given 56.7 grams. So in my brain, I'm saying I'm going from sodium to hydrogen. So we're going left to right. So if I wanted to label my molar roadmap up above, I would be starting down here with grams of chemical A. There's my grams of sodium. The only place I can go from there is the middle, which is moles of sodium. And at this point, I have 3 choices. I can go up to liters of sodium, down to molecules or atoms of sodium, or I can go over to a new chemical. Well, indeed, they wanted us to switch chemicals, so we are going to hoof it over here, 2 moles of our new chemical, which was hydrogen. And we're going to stop because they asked us for moles. So again, it's 3 steps, but just in a different order. So I know I'm going to need 3 tracks. 1, 2, 3. I put my given in the first track, 56.7 grams of sodium. And I diagonal down, grams of sodium. The only place we said we could go up on our map from grams was to moles, so that's the old step. Nothing new there. So at this point in the old step, moles always had a 1. Grams always came off the periodic table. Sodium's molar mass is 22.990. So nothing new yet. Our grams of sodium cancel with our grams of sodium. We've got moles of sodium now. So we're going to put moles of sodium. Then we're going to say, where are we going? We're going from moles of sodium to moles of hydrogen, and we're going to be using those coefficients for our ratio. So it's so tempting right here to just want to put a 1 here, and you can't do it. Wait and do the numbers last. Always do the letters first. I'm switching chemicals, so I'm going to switch colors again. I'm going to moles of hydrogen at this point. So what I'm wanting your brain to notice is that you've got moles on top of moles. This tells me that this is not my 1 mole step. This is reminding me, oh, I've got to go find that mole to mole ratio. Where do I get my ratio? From this 2 to 1 coefficient. So I have to use my coefficients here and say that there are 2 moles of sodium required to form 1 mole of hydrogen. So again, it's just a coincidence that there's a 1 there. Sometimes there will be a 1, sometimes there won't. Our moles of sodium cancel with our moles of sodium, and we're ready to calculate. My calculator says 1.2331 blah, blah, blah. And so I only need 3 significant digits, and so it's going to look a little like this. 1.23 moles of hydrogen. Whatever in this last box always gets slapped onto our answer. So that's that. Let me show you a big mama. Here we go. In example 4, it says what mass of oxygen, so I'm going to go label oxygen with how many grams, is needed to completely burn 137 grams of butane. And they told you right there, butane is this. They didn't need to tell you that because you know it's not water, you know it's not carbon dioxide, and you know it's not oxygen. Just pointing that out. Little common sense goes a long way. 137.9 grams of butane. So in this example, check it out. We're going to be going from here, our given, right next door to oxygen. So we're never going to cross that arrow at all. If we looked at our molar roadmap and we plotted this, we started down here with 137.9 grams. So that's grams of chemical A. So we'll label that. We're starting here at grams of butane. The only place to go from there is to moles of A, which is moles of butane. Then, since we want to switch chemicals, we're going to jump across to moles of oxygen. So this is our oxygen side. But we're not going to stop there because they asked us for grams down here. So we have to go one more step down to the bottom to get grams. So now if you notice, I've got 1, 2, 3, 4 things circled on my map. That means I'm going to need 4 tracks. I'm going to have to write small. So we start with our given, which was 137.9 grams of butane. Butane's the same chemical in a cigarette lighter, the liquid that you slosh around and light on fire. And we're going to go down and say grams of butane. And if we consult our map, we're going from grams of butane to moles of butane. This is an old step, nothing new here. We know that moles always gets a 1. Butane is going to get his molar mass, which happens to be 58.124. Added all that up. Our grams of butane cancel out. We're at moles. We consult our map and say, where are we going to go after moles of butane? We're going to jump across to our oxygen side. So this is our mole-to-mole ratio step. So we're going to go from moles of butane to moles of oxygen. So since we're switching chemicals, remember how to do that yet? We're going to look at our coefficients. It's a 2 to 13 ratio. So we're going to put a 2 at the bottom with butane and a 13 on top for oxygen. We're not done yet because we know we needed a 4th track. So we diagonal down moles of oxygen into grams of oxygen. This is our old step. We're down here now, going from here to here. So we should know when we're on one side, moles always gets a 1. Grams is your G units. Take 15.999 and double it. Our moles canceled out over here. Our moles canceled out over here. And we're ready to calculate. And we get a whole lot of digits in our calculator. But with 4 sig figs, it ends up being 493.5 grams of oxygen. Don't forget his little 2, since he's a Hofbrinkel. So you've done stoichiometry. You've seen 4 different examples. We just stuck with grams, moles, and mole ratios. We didn't involve liters. We didn't involve molecules. Indeed, we could, but we're going to start off a little bit slow. So you know a lot. You've seen a lot. Process. Watch the steps that you don't understand when you get to class. Probably on Tuesday, since of our crazy half day on Friday, we'll hit this with the ground running in all of my classes. So see ya tomorrow, guys.